For this exercise, I've designed a pipe reducer that will go in this existing assembly. I'd like to run a test on the reducer using Simulation Express to simulate the pressure inside. To do this in Express, we'll need to know how much pressure to use for the load. But how would you know how much pressure will be applied to the inside faces? Well, one way to find this out is by using the full version of SOLIDWORKS flow simulation. With a simple study that accounts for the inlet, outlet, flow rate, and the type of material flowing through it, we're able to quickly find out how much pressure the reducer will experience. For this exercise, we'll be using a pressure of 1500 psi. To get started, I'll open Simulation Express. Since I'm interested in finding the maximum stress in units of psi, I'll go to Options and select English for the units to be displayed in the results. To get started, I'll click Next to apply a fixture to the reducer. So how will this part be fixed? Well, it'll be bolted down to the surrounding components around the bolt circles on both sides of the reducer, but the outer faces will also be in contact with the surrounding flanges. So how do we simulate this in Express? Well, in full versions of simulation, you could let the software figure out how it would interact with the surrounding components. But since we're limited in Express to the fixed geometry type of restraint, I'll start by just fixing the faces of the bolt circles. For this example, I'll select the bolt circles on one side of the reducer and click the green check. For the other side, I'll add another fixture. Since all of the fixed restraints will be applied at the same time in Express, I could have just as easily added all of the bolt holes in a single restraint set and would not affect the results, but this might make it easier to come back to these later. Here in the study tree, you can see both sets of fixtures. I'll click Next and move on to the load section. For this exercise, we need to create a pressure load. I'll click Add a Pressure. For my load set, I have to select the interior faces of the reducer. Now you probably noticed in the flow simulation example how the pressure actually changed as the material flowed through the reducer. If the pressure changes were significant, this might be a good example to apply multiple load sets using a different pressure load on each face. If this test was being done in the full version of simulation, I could have actually imported the data from the flow simulation to let SOLIDWORKS take care of the true pressure change throughout the reducer. In this case, the pressure change was negligible, so for simplicity's sake, I'll be using a single load set on all three interior faces. I'll select the three inside faces. For the pressure value, I'll type in 1500 psi and click the green check to finish adding the load, and you can see it listed in the study tree. I'll click Next to move on to specifying the material for the reducer. For this study, I'd like to apply a copper material. I'll click Change Material, browse for the copper material, click Apply, and close the material dialog box. I'll click Next, and SOLIDWORKS tells me it has enough information to run the analysis. I'll click Run the simulation to run the study with the default mesh settings. When the analysis is complete, SOLIDWORKS shows an animation, and you can see the reducer expands due to the pressure load. This makes sense given the loads and fixtures we applied earlier, so I'll click Yes to continue viewing the results. First, let's have a look at the stress distribution. Here, you can see that the maximum stress is occurring around the bolt holes of the flange. This might be artificially high here due to using the rigid fixed restraint type, but if you're interested in knowing what the stress is in the actual reducer in the area where the most displacement took place, be sure to pay close attention to the values in the legend. You can see the green color here represents a value of around 15,000 psi. Next, let's take a look at the displacement results to see how the model deforms under load. Here, you can see that the maximum displacement is occurring around that widest part of the reducer. Also notice there's some strange deformation around the flanges of the bolt circles. If I zoom in close to one of the bolt holes, notice how the fixed restraint kept the bolt holes perfectly rigid, while the material around them deformed. Again, in the full version of simulation, this could have been more accurately represented by the true interaction of the other components. You can see in the task pane that Simulation Express reports that, based on our pressure load, the reducer has a factor of safety of over 1.3. Since Express is a free tool with some limited functionality, such as the fixed restraint, It never hurts to try a couple of variations of the tests, in case you don't have a full version of simulation available. For this exercise, I'd like to try one variation of the study by fixing the outer faces where the reducer connects to the surrounding flanges. This might lead to different results and perhaps make the deformation more realistic. To make changes, you can always go back to a previous step in the wizard. You can always make changes to the study by simply interacting with the items in the study tree, no matter which step in the wizard you might be in. Here, I'll right-click the first fixture in the study tree and select Edit Definition. I'll add the outer flat face. I'll click the green check and do the same for the second fixture set. With the faces restrained, I'll rerun the study. The animation again looks good, so I'll continue. SOLIDWORKS now reports a factor of safety of almost 2.5, much safer than last time. If we look at the stress distribution, we can see the flanges are much more rigid due to the restrained flat faces. And now, the maximum stress is at the wide part of the reducer. Again, pay close attention to the legend. The red areas shown on the plot are around 15,000 psi, nearly the same value we had before. So why is 15,000 shown in red this time, but was shown in green before? Well, keep in mind when looking at the color code in this legend, don't always assume red is bad and blue is good. These colors simply represent the maximum and minimum stresses in the study and are strictly used for visualization. You should, however, always be aware of how these values compare to the yield strength of the material, shown at the bottom of the legend. Before concluding this lesson, do you remember how the first iteration of this test resulted in a factor of safety of about 1.3 when just the bolt holes were restrained? And the second iteration resulted in a factor of safety of about 2.5 when I restrained the outer flat faces? Well, both of the tests showed that the stress in the wide part of the reducer was around 15,000 psi. The factor of safety in the first test might have been artificially low due to the extra high stress in the bolt holes, whereas the factor of safety on the second test might still be artificially high, because the fixed restraints still may not accurately represent the true interaction of the surrounding components. As I've mentioned throughout the course, the full version of simulation has the right tools to accurately simulate the true behavior. But since both iterations here in Express provided the same value of around 15,000 psi stress in the wide part of the reducer, this gives me confidence in the stress values in that region that we saw in both iterations. In fact, if I compare it to the results from a test in the full version of simulation, I can see the values are in fact very close.